Hi, my name is Wittawat. I'm going to present our work on testing goodness of fit of conditional density models with kernels. Okay, so here's the problem setting. We are given two things. The first one is a conditional density model, py given x, where x and y can be multivariate. And the second is like a set of IID observations taking the form of xy pairs following an unknown distribution ry given x times rx, where ry given x is just the true conditional distribution that we don't know. And we want to test whether p is the same as r, whether the model is the correct conditional distribution or not. For some marginal distribution rx, then we don't really care. So an application of this work would be to test goodness of fit of a trained regression model with, for example, Gaussian noise. If you use the Gaussian noise, then py given x would take this form, where f of x is the conditional mean, and for some variance function. So here's just an illustration. But in general, the conditional model that we test doesn't have to be a regression model. It can be any arbitrary conditional distribution. Okay, so there are quite several related works on kernel-based testing of for distribution comparison. Starting from the work of Gretton and colleagues in 2006, proposing the MMD. And there were several extensions from that time. But all these address the question of comparing sample and sample, right? Two-sample testing. But there was another direction where the goal is to compare a marginal model, Px, and a sample. And yet, there was another direction where the goal is to compare two competing marginal models, P1 and P2, versus the real sample to be observed. So all these works only address marginal distributions, but in our present work, this is, to our knowledge, the first time that kernel-based testing of a conditional model is studied, and there's no need to do there's no need to do density estimation as an intermediate step. Okay, so we contribute two statistical tests for this purpose. The first one is called the kernel conditional Stein discrepancy, KCSD. The statistic is nonparametric, meaning that it can test a wide range of differentiable models, py given x. It can be estimated easily. There's no need to even sample from the model. And third, the test doesn't need the normalizer of the model, which is usually intractable to compute. And the second test that we propose is called the finite set conditional discrepancy, FSCD. It is actually an extension of the first test, where it also returns an interpretable result. So what I mean by this is, let's say this is our problem. So the second test can return a point V in the domain of X that indicates where the data and the model differ. So for example, in this case, that would be here, because this is where the data and the model differ a lot. Okay, so how does it work? So to explain the first statistic, I'm going to use this as a running example throughout. So here we consider a regression model where the conditional mean is a quadratic function, is x squared, and the variance is constant. This is for the model. But for the true distribution that generates the blue points, that's R, it's almost the same as the model, except the variance shoots up at x equal to 2. So at x equal to 2, there's a kind of big variance here. So on the right, here's a plot of the variance function. It's 1 almost everywhere except at 2, where it is very high. So one thing to note from this slide is that P and R differ only around x equal to 2. Okay, that's the key point to remember. Okay, so how does it work? The first step to compute the statistic is we need to compute a so-called conditional Stein witness function, G, as a function of y and x, and it has the following property, which is that for each x, gy given x is a zero function, if and only if py given x is the same as ry given x for all y. And this holds for a particular x, okay? So this is what it looks like. So G is flat almost everywhere else except at x equal to 2, where there's some activity. And this is what we want, the first step. And it turns out if we want this, one way to compute it would be to use this, right? G is given by an expectation of C function. Like C function is defined like this. And L here is a positive definite kernel on Y, which you can choose to be a Gaussian kernel, for example. And C function depends on the gradient of the log density. But all this can be computed, okay? Okay, so now that we compute this, it is known, actually, that if L is nice, so meaning that it is actually C0 universal, then we get the property that we want. Okay, so just to show you that it is indeed the case, it's the same plot in 3D where we see that it's flat everywhere else except at x equal to 2. Okay, so next, once we have this G, we need to check that it is indeed the zero function for every x. Okay, not just x that we observe, but really every x in the whole domain. And to do this is the tricky part, right? Because the region in the x domain that reveals the difference between P and R can be small. Like in this case, it's kind of small region here. So our idea is to spread out the signal, okay? So we take G, small g, multiply it with another kernel, kx. Okay, this is another kernel on x now, positive definite kernel. And then we take the expectation with respect to x. Okay, so if you can't imagine what this is, then imagine that k is a Gaussian kernel. Just think convolution, okay? We take the original small g, do this operation, then we get a new function, still as a function of x and y, but it's kind of broader, right? Because we do the convolution. Okay, so third step, I'm going to call this new function big G. So all we need to do is to take the norm of this big G, norm in the reproducing kernel Hilbert space that the G function lives in, okay, and square it. And that is our statistic KCSD. Okay, so essentially by taking the norm, we summarize this whole function into one scalar number. And indeed, we can prove that this quantity is actually zero if and only if P is R everywhere. Okay, this is nice. Okay, but then the next question is, can we compute it? And the answer is yes, we can compute it by using this expression. It looks complicated, but it's actually not. It's just double expectation of some function that you can compute. And key point to take away is that we can replace this E with empirical average, and it depends only on the gradient of the log density, which is actually independent of the normalizer. Okay, so the take-home message is that we propose two statistics. The first one is what I just explained. It's actually, we didn't have time, but it's actually good for detecting spatially diffuse differences. But the second statistic is good for detecting local differences. If you'd like to know more, please check our paper, and please feel free to send questions or comments.